Alright, welcome back. Today we're going to go ahead and pick up the first two sections of Chapter 4. Um, should be Chapter 3.4 we already covered on the geometric and binomial distributions. So this will just be Chapter 4, so kind of a shorter lesson today. Alright, so here's the idea. Now normally we don't have a population, or I should clarify, we do have a population, but it's just impractical to sample everyone in the population. If we do that, it's called a census, and it's very hard to do. Of course, the U.S. tries to do one of these every 10 years to actually poll everyone in the population. But what's more practical is to go ahead and take a sample. Now, we had already talked about the mean and standard deviation. When we're talking about a sample, what happens is we call this mean x bar. When we're talking about a population, we call this thing mu. So these are just both the means. When we have the variance in a sample, the notation is s squared. When we have variance in a population, it is sigma squared. And then we can also talk about standard deviation. So here it's just sigma, and here it's just s. So more often than not, we don't know these population things. These population parameters is what we'll call them. Rather than that, here's the idea. You've got this whole population, so what instead you do is you try to do this as random as possible. We get a point there, we sample a point here. We just do a couple of random points there. And we pick up this sample. And what we do is, the mean is very easy to calculate from the sample. We just add them up and divide by the total. And this will give us an idea of what the population is. And we have similar approaches as far as variance are concerned. We can take the variance of this sample and use it to project what we think the population variance is, and similarly with the standard deviation. So we do call these things point estimates. So x bar is a point estimate of the actual population parameter. And what we mean by point estimate is, well, the population mean isn't going to change. It's the same every time. But as we take different samples, if we sample this again, our average or mean, it's not always going to be the same, right? If I do average lecture video here is an hour and 5 minutes, and you only look at 2 or 3 of them, you know, it depends on which 2, 3 you're looking at. You might find an average that's a little bit above that or a little bit below that, because they're certainly not all the same length. And then the variance of those are all obviously going to depend from sample to sample as well. So these samples are changing. So sort of what good is this? Well, we have this famous theorem called the central limit theorem. We're really not going to apply it too much, at least in words anyhow, or algebra. But here's what it says. X bar. So keep in mind what x bar is. It's just taking a sample, x1 plus x2 plus all these, all the way up to xn. So you take a sample of n. So if n is 5, you have x1, x2, x3, x4, x5, all divided by 5. But I'm going to use n here because n could be anything. The central limit theorem tells us that from here, we have a population. If we take an infinite size sample here, as n gets larger and larger, this point estimate even though it's going to change from sample to sample, if we take a very large sample, it's going to be close. If we take a larger sample, it's going to be even closer. So while it's not going to be exactly the population mean, the larger sample we can take, the more accurate of a estimate on this population we have. So that's really what the central limit theorem is good for. It tells us this thing, but even more so, it tells us that this is going to be normally distributed. So if we have some sort of population, some kind of random variable which is normal, so it tells us x is a normal random variable. Then what's the distribution of x bar? X bar is also a normal variable with the mean x bar, comma, and here's where it matters if you're taking it from a population or a sample. So for now, we're going to go ahead and assume we're taking things from a sample. So the standard deviation is actually going to be s over the square root of n. So this is the mean, and this is the standard deviation. Sometimes we'll go ahead and call this thing standard error. So you might see it written this way. The standard error of x bar is equal to s, the standard deviation of that sample, taking these same 5 numbers or same n numbers, and dividing by the square root of n. This will give you a standard error, which is the error of the normal random variable x bar. So still looking at the central limit theorem here, what it tells us is that if we have the population mean is here, x bar is normally distributed. So this is a normal distribution function I've graphed here. And what it says is, sure, we can take one sample, we might get an x bar from our sample that's actually a little bit greater. We might get one that's a little bit lower. But the point being is, generally speaking, you're a certain, I guess, width away from it, or an error away from it. We call this thing a confidence interval. And so let's go ahead and say that this is n equals, we just took a sample of 10 here. We might see that if I take a larger one, what happens is that the probability of being farther away from this mean gets smaller. So as you increase your n, you get closer and closer to this mu, and so it gets more accurate. So that's actually what's happening with the central limit theorem. Okay, so you have x bar is distributed in these normal curves here. What we're going to be doing instead is we're going to be using x bar, our point estimate, to get an approximation of mu, our population parameter. So here's what we'll do. We'll take x bar and we'll look at this thing. We can use the normal distribution to find an interval. So we can find a point over here and a point over here so that these points are symmetric and contain, let's say, 95% of the data. So here's the translation. If x bar if this contains 95% of the the data here, 95% from here to there, what we can do is we can say, okay, well that means that there's a 95% chance that the population mean falls within this interval. And, and then you can kind of see that it's not quite accurate to show this first. What you're really doing is you're using the idea that these samples are normally distributed around the population mean. And if I create a 95% confidence interval here, it gives me an idea of where my x bar is falling. So we're using that same interval then, the same kind of idea, that same interval. And well, if it misses it by this much out to the side, x bar is out here, then the same thing happens. Well, x bar is too far to the right, so the mean is still within this interval. If x bar misses to the left, well then on here, the mean, the x bar is missed to the left and the mean is still contained in this interval. So that's about all the theory we'll get into as far as the central limit theorem. So just know that if I find these 2 points where 95% of the data lies between these 2 points, that means that the area underneath this curve is 0.95, then I've found a 95% confidence interval for my population mean. So again, we're taking this sample and using it to get an idea of what my population parameter is. So I'll write, I guess, parameter. All right, so let's move on to an example. So here's the example. We've got 100 students, and their average is 1485 on the SATs. And we're given that a standard deviation of 250. So we want a 95% confidence interval for mu, for the population. So we'd like to kind of say, well, given this, can we find an estimate, assuming that these 100 students are random across the U.S., find an estimate for the actual U.S. average on the SATs. And so here's how this will work. Indeed, we have this kind of thing going on, where in the middle we have 1485 because that's our x bar, right? The standard deviation is just going up 250 at a time, so we have 1510. Well, I'm sorry. I'm getting ahead of myself. Let's look at the standard error of this thing. The standard error of x bar, so x bar is 1485. The standard error of this thing is going to be 250 divided by the square root of n. N here is these 100 students. We have 100 of these. So our standard error is 250 divided by 100, and ultimately this gives us, well, I'm sorry, not 110. Ultimately, our standard error is 25. Now I can go ahead and make it 1510, 1535, and 1560. 1460, 1435, and 1410. Just to give you an idea of what's going on. So here's the sample that we took right in the middle. We want to find something to the left of it and to the right of it that contains 95% of our data. Okay. Alright, so before we do this, let's put this to the side and come back to it. Real quick, if we're looking at the standard normal curve, which is a 0 in the center, 0 is the mean, 1, 2, 3, with a standard deviation of 1, and I wanted you to find a 95% confidence interval, that means I want some kind of point either side of here so that everything in between here, the area here is 0.95. The way to do that is to recognize that these are symmetric, right? So it's symmetric across this 0. So the area here is the same as the area in this white space. So looking at this, I want this area plus this area to equal 0.5%. I'm sorry, 5%. So I'm looking for, I guess, we call this region 1 and this region 2. Region 1 plus region 2, I want this to be 0.05, which is 5%. But really, because they're symmetric, it's just 2 times R1 equals 0.05. We have a name for this 0.05, sort of the complement of this 95%. If this is what we're confident on, then what we're not sure of are these two regions, and this sort of makes up this thing they call significance level. Sometimes we denote it as alpha. So our alpha here is 0.05. So if our confidence level is 0.95, our alpha is 1 minus 0.95 to give us 0.05. So we've got these two regions equal to our significance level, our alpha. So to solve for this, region 1, how much area is in there? It's half of it, right? Simple as that, right? To define these confidence levels, really what we're going to do is we're going to be looking for alpha over 2. We're going to be finding what we'll call z star of alpha over 2. So the way we'll do that is we do need to use our book. And you can find in your chart, this is the t distribution, we want the z distribution. So we want to find, in this case, it's 0.05 divided by 2, which gives us 0.025. So we're looking for 0.025 in here. These are placements on the outside. The area is on the inside. Okay, simple as that. So we're looking for the area of 0.025. So as we go across here and we're looking through, you'll notice that the numbers get larger as you move left to right, and then it drops down and continues to get larger. So you don't need to do all that. Try to find it your best. This is 0.0228. That's too small. Keep going. Too small, too small. Eventually you find 0.025, which is exactly what we're looking for. Right there. If I read these things off, this says negative 1.96. So negative 1.96 is what this thing we call this z star value. So here happens to be negative 1.96. So what does that mean? It means if I want to find on the standard normal curve where 95% of the data is, this would be negative 1.96, and off to the right I'd have positive 1.96. And it's as simple as that. Okay, so we're going to kind of take this idea and apply it to this problem that we had already started. So let's look at this 100 students and their average. Right? So here's what we'd like to do. We'd like to go ahead and find sort of a similar point out here. Let's switch over from pencil. Note how well that will show up. And right now it's a little hard to do to find this thing. So what we'll end up doing is we'll sort of transform this data using the z-scores. So normally we have what? Z is equal to x minus mu divided by sigma, where x's are observed. It's going to look a little different now. Now we're talking about x bar minus the mean divided by the standard error of x bar. So the formula for this actually ends up being x bar minus the mean divided by standard error. Here was I guess sigma divided by the square root of n, depending on what you were given, sigma over the square root of n or s over the square root of n. Okay. So if you rearrange this, it's not too hard to see. If I multiply both sides by this denominator, I'll have rho divided by the square root, sigma divided by the square root of n times d is equal to x bar minus mu. And if I add mu to this side and subtract this, I get mu is equal to x bar minus this sort of thing. And it's sort of the thing that, yes, I can miss it on the right side, I can miss it on the left side. So our formula to find the confidence interval is precisely this. We give our point estimate plus or minus z star of alpha over 2, because our significance level, these are these things we're unsure of, we divide it by 2 because there's 2 tails. And this is times our standard error. So if you'd rather, it's just as simple as our confidence interval is a point estimate plus or minus the standard error of our point estimate times z star of alpha over 2. And this is what we'll use. Okay, so we have this 100 students, their average, their standard deviation. Let's go ahead and use the formula. So we can kind of see how this is going to work. The point estimate is just this x bar we found is 1485 plus or minus, because I can miss on the right side or the left side. The standard error we found was 25. And z star here, we were talking about 95%, and we already found what z star of 95% is. It was 1.96. So some of you out there might say, okay, we saw negative 1.96. It doesn't matter if you use positive 1.96 or negative 1.96 because of this plus or minus. 25 times 1.96. This gives us 49 here. 1485. So what this means is we have 1485 minus 49, and we also have 1485 plus 49. So again, if you just had a negative sign here, if you had used the negative of that z star, what would happen is this would be negative, and you'd have instead 1485 plus 49 here and 1485 minus 49 there. It's not a huge deal. But in general, we'll just kind of go ahead and take a positive to that T star. Okay, so what does this give us? It gives us 1485 minus 49 is 1436, and it gives us 1485 plus 49, which gives us 1534. So I'll go ahead and write it this way. This is then the lower bound, and this is the upper bound. And if I put these two together, you can kind of see, so 1436 is about here. That's the lower bound. And 1534 is just before that. So about there, 1534. So again, what did we do? We took the mean of our sample, and we found with 95% certainty that between 1436 and 1534, our actual population mean is somewhere in there. So we can say with some certainty, 95% certainty, that the students in the US average somewhere between 1436 and 1434. And so if you go back, of course I'm not going to ask you to derive any of these things, but just look at this confidence interval formula. The point estimate plus or minus the standard error of that point estimate times E star. So it's sort of like you have the point estimate, and it seems reasonable that we're going to be adding something to that and subtracting something to that to find this interval. Okay? So at least that way you can kind of, should help you memorize this thing. Let's do another example from start to finish. So this is 4.17. We want to go ahead and find 99% confidence interval of the runner's age. So we're given that scratch that. Let's just move on to this one. So this will kind of give you some idea of how this is actually used. Coke is going to claim they put 300 milliliters in a bottle of Coke. Okay, so that's their claim. That's what they're selling. We want to kind of see about that. So what we do is we sample 50 Cokes, and we find an average of 298.4 milliliters. Now again, because averages can be a little higher, a little low, this doesn't mean anything to us. Let's go ahead and look, and also we're given that the standard deviation of our sample here is 4.2 milliliters. I'm going to go ahead and tell you that this distribution is normal, and so that allows us to use the central limit theorem. Let's go ahead, and this time, let's find what kind of confidence interval. Let's find a 90% confidence interval. You'll typically see 90%, 95%, and 99%. So you'll probably get used to these numbers. 95% is 1.96. 90% is 1.645. you'll get used to these things. Okay, so what is the confidence interval? It's the point estimate, which is our x bar, plus or minus the standard error of our x bar, because we're talking about average here, right? This is our mean, finding estimate of, or population mean. Standard error of x bar times z star of what? Of alpha over 2. So alpha here is our significance level. So let's go ahead and label this stuff. Our sample of 50 cokes, this is n. Our average, this is of course x bar. And our standard deviation, this is from a sample, so we're going to go ahead and put f. You know what, let's go ahead and assume this actually, somehow we actually know that the standard deviation is from the population. Let's go ahead and use sigma. Alright, so we're asked to find this. Let's go ahead and, oh yeah, one last thing. What is alpha? If we're 90% sure of this thing, that means we're 10% unsure. So 100 minus 90, or 1 minus 0.9, gives you 0.1. Our alpha that we're looking for is 0.1. Okay, so filling this stuff in. X bar is 298.4, plus or minus the standard error of x bar. Well, keep in mind that that's really a sigma divided by the square root of n. And let's go ahead and fill this in. Z star alpha over 2. Alpha was 0.1 divided by 2. Continuing along, 298.4 plus or minus 4.2 divided by, we're told that we have 50, so n is 50, square root of 50, times z star of 0.05. Okay. So moving along, let's see, 4.2 divided by the square root of 50. This does give us 298.4 plus or minus 0.594 times z star of 0.05, and we're asked to find this. So of course we have to find our book again. And we're looking for the area inside, so we're not going to, it's tempting to just go ahead and look for 0.05 on the outside here, but don't do that. That's not, these are the locations on this thing. We're looking for the area. So we're looking inside, 0.05, and don't get confused, there are these 0.0005, that's not what we're asking for. It's not negative 3.2, or I'm sorry, it's not negative 3.32. We have to keep going until we find 0.05. And we don't have it quite. If you look across, it gets larger. We have 0.0495, and we have 0.0505. So we don't quite have it. It's somewhere between these two. So what we'll go ahead and do is we'll just go ahead and pick the center. So this is negative 1.6. This one's 5, and this one's 4. So negative 1.645. How about that? So negative 1.645. Just the average of those two. So as promised, it is 1.645. Multiplying these two together, we have 0.594 times 1.645. You get 298.4 plus or minus 0.97713. So we have 298.4 minus that bit, 297.42. and plus vector. 299.37. So again, this is the lower bound, of course, the smaller one, and this is the upper bound, the larger one. So on your quiz, when I do ask you these things, the way I'll ask you is I'll tell you find the lower bound, so we'll be asking this number, and the next question might ask you for the upper bound or something like that. Okay? And again, it might be useful to know that for Z star, if you're looking for confidence interval, if you're looking for, let's see, 90% is 1.645, 95% is 1.96, and actually I can't quite remember what 99% is. Look that up real quick for you. It's negative 2.75. We'll call it negative 2.75. It's another one of these fractions. That's good enough. So these are typically what you'll be using. So if you're asked to find 90%, your Z alpha over 2 is this. If you're asked to find a confidence interval of 95%, Z alpha over 2 is this. Confidence interval of 99%, Z alpha over 2 is this. So the homework for this section really should not be that bad. Basically just use that formula. This one, make sure you do just go ahead and use this. And make sure you know how to calculate this. You should be alright, okay? So best of luck to you out there then. Again, if you have any questions, let me know by email. And do make sure that you are clicking through on the site to actually get through to these videos. You do need to actually click the true or false question to get attendance for this class. So I noticed that I think one of you had not done that. So of course, you'll see these things off to the side on the YouTube. Don't be tempted to click there, or you can click there, but just make sure you do go onto the site and click through there to answer that true or false question. Otherwise, you won't get credit for watching the video. Alright? So thank you very much, and I'll see you next week.